All right. Hello, everyone, and welcome to Module 4, where we'll be talking about Bayesian networks and decision trees. We'll get into that a little bit more in a moment, but the short of it is the assignments are a little confusing in this one, and so is the material we cover. So we're actually talking about kind of two different things. Bayesian networks are a thing, a particular thing, and so are decision trees, and they're not the same thing. That's where this module is a little confusing, but we'll go with it and get through this, and we'll be fine. So you're asked first of all to talk about the theory of Bayesian analysis and probabilities and so on, but you're also asked to do decision trees and the theories behind them, and understand those are kind of two different things. Bayesian networks are very different from a decision trees. They're constructed different ways. They yield different results. They have different things that make them desirable. So you also need to be able to interpret the results of a decision tree. You develop a decision tree in one or more programming language, two if you want to do well. And then you'll make sure you talk also about the theories about them. So Bayesian analysis, Bayesian I would talk about if I were writing this Bayesian networks, and then decision trees and kind of what those things are. Compare, contrast, if you will. So a review. It's always good to review Bayesian stuff or statistics stuff. Basically, the general idea here, and we're not in we're in a data science class around the application of statistics, not a statistics class. But the basic idea here is the more you know, the higher your confidence becomes in being able to predict something. So, and that's probably this whole concept of A given B and the relationship that those things have together. Quick review. So what's a Bayesian network? And it's basically a graphical representation between nodes, not that dissimilar in a way, between the Markov models that we've talked about in the past. The difference here being, though, the idea of the sprinkler coming on and it being cloudy has a certain amount of probability, and probably not a 1 in this case. So a better example, and we'll talk about this, is let's make a deal, right, in Monty Hall. So the Monty Hall problem is a pretty well established Bayesian topic. And it's counterintuitive. It's the scenario, if you're not familiar with the game show, is that you're a contestant on a prize show, and there are 3 doors, and you choose a door. Behind 2 of the doors is a goat, and behind one of the doors is a car. You clearly want the car unless you have a thing for goats. So you select a door. And whenever you select a door, if it is not, basically the door is opened after you've selected it. Assuming it's not the car, you are then given a choice of potentially, and it's not the goat, you're given a choice of selecting a different door or not. So you've got initially a probability of 1 in 3 of getting something good. But oddly enough, rather than it being at the point that 2 doors remain, thinking that your probability is 50-50, the fact that you have some new information, namely that it wasn't behind the door that was opened, then so you pick a door, he picks a door, opens the door. The car is not behind the door, so you still got a chance at the car, right? So naively, you might think, well, it's 50-50 chance that it's behind the door I've picked, but it turns out it's actually you're better off to switch doors, and your odds go from what you think of being 50-50 to actually 66%. So it's kind of counterintuitive, and that's part of the reason why it's talked about. So let's go ahead and open this up. One of the things I did find that was useful for this experience was, let me get the right window, was that the use of pomegranate as the library. Generally speaking, in these sort of courses, we spend a lot of time in scikit-learn and variations thereof. But in this particular scenario, you're better off doing a different tool set. Let's wait for this to open. There we go. So pip install pomegranate if you don't already have it. If you already have it, then obviously no point of doing so. So we'll go ahead and clear this out. And this is something I borrowed obviously from the pomegranate documents because it is a common problem and a good example of Bayesian networks. And so it starts off here, and I'll try to tell the story again a little better. The idea is that the Monty Hall problem is a game show where a guest chooses one of three doors when an unknown one with one of them having a prize behind it. Monty opens another non-chosen door. So you pick a door. I want door number 1. He picks between 2 and 3 and opens door number 2 or 3 that doesn't have a prize behind it. So he knows where the prizes are, so he just knows what door to open. And ask the guest if they would like to change their mind. So you've picked a door. I want door number 1. He opens up door number 3 and there's not a prize. You would think 2 doors, 50-50 chance, but it's actually not. So many people find out that it's basically if you switch doors, your odds go to 66%. So better odds if you switch, which counterintuitive, I know, but the math works out. So to go through this, to kind of show it, we do import math and import pomegranate. And then we create the distributions of basically we start off with A, B, and C being a third. And then we construct the probability table. And then we can take a look at the states. So we create 3 states and we fill the network in. And then the transitions. So we're constructing kind of the diagram, and then essentially you bake it. This is a pomegranate thing to where you're kind of creating it, and then you can print out the states. And this one, I got to remember to do this because it's a handy way of presenting something that's an enumeration. You're doing a join off of a tab. So you take the tab character, do a join, and then inside of that you've got what's essentially an array, right? So kind of cool. I need to remember to that one down the road. So here we start off, and we see what happens whenever the guest chooses A. So the guest picks door A out of ABC. Probabilities are basically 33% that chance that they've got something good. And then basically you got a 50-50 chance that Monty is going to pick something other than A because he can't pick what you picked, right? So it's one or the other. The difference, though, is he knows where the prize is, right? He's not going to pick the car. So he opens up the non-prize door, and so we can then say from observations that the guest is A and Monty is B, we can construct some beliefs from that based upon these observations, and then print them out again, doing this clever sort of thing with joining off of strings and then formatting across some various values. And so we end up saying that the guest has picked A. The prize distribution is 33% chance that it's at A. So your odds are very slim compared to 50-50 that it's on the door you have. It's actually 2/3 chance that it's somewhere else. And so you know that it's not behind B because he picked B, so it's either behind the door you have or another door. And so we can see what happens if the host chooses B, and so on. So we go to the next observation, and then we can train the network off of what we see. Again, and print out the odds of the various combinations. And again, gives you some sense of the distribution. So this is an example of a Bayesian net. So Bayes nets in action, quite distinct from a decision tree. So also the Monty Hall problem is a very common one. The link down there is a good example of it. Let's drop out of this and so I can get to it. Or better yet, make it clickable. And so this is a good example of going through it. Brilliant.org/wiki/monty-hall-problem. And we'll just get past it so we can, sure, yeah, you can know who I am. I don't know if you need to know that. All right. I got it, go away. Shoo. Try that again. Okay, so back to the discussion. Goes through the various probabilities, the Bayesian stuff, and it all kind of hinges on the fact that it's not a truly random thing, right? The game show host knows where the prizes are, so it counts on people feeling compelled to stick to the choice that they've made, and so people are going to be tempted to do that rather than switch over to something else, which would probably be the more advantageous. Now, back to what is a decision tree. Probably saw this if you've taken clustering or classification, not clustering, classification. Supervised way of learning that basically continuous splits until a terminal state's reached. So you use it because it's easy to understand and it is very explainable. You can look at a decision tree and make sense of the rules and kind of does it jive with reality, right? And that's one of the reasons we use decision trees. Bayes are a way of doing things that you understand there is some probabilities and so on. And to confuse things even more, you've got naive Bayes versions of classification, which is not a Bayes network, but it's using Bayesian concepts of assuming things are independent. So common approaches that are used whenever you're constructing a decision tree are ID3, CART, and CHAD. CART is available in R and Python, very commonly used. So to demo a decision tree in R, we'll start off with R first. Basically, hopefully this works. We'll see. Yes, it did. So we're basically loading up our same biz rate, we're reading the CSV, and doing the partitioning of the things that are not the bad, so knowing which is the bad dead and so on. Go ahead and plot it, and here's what the tree actually looks like. So it does it that quickly of the R part, and it creates the tree and shows you the root and the basic ways of going of debt. MDET Inc. versus being less than and greater than and so on. So less than 45.15 and so on. So you can basically see as we're constructing a tree. This is essentially kind of the one of the things you're asked to do. You're not actually asked to create a Bayesian net in the assignment this week. You're asked to create a decision tree, but talk about Bayes networks, which is kind of interesting. So with that, we'll switch over and take a look at that in Python. And probably already have that installed, probably have that installed. So let's just go ahead and clear the output and run through it again. So my typical thing of finding out where my home directory is or the data directory for this particular assignment, import numpy pandas and scikit-learn. From that we get the tree. We have a file and we combine it together to actually load the file into a read CSV into a pandas and call tree. Then we basically do our separation of our df x and df y of the labels versus the features, and then do a decision tree classifier off of that. So we say that we're going to go a max depth of 3, and we're going to make it essentially fit, so generate the tree. And then now we can take a look at what the tree looks like. Feature 21 greater than or equal to 50, or 50%, or 0.5, or 45.15, which sounds a little familiar. If I remember, this was 45.15, and so on. So kind of interesting. We're lining up there. Probably the same algorithm, and so on. And then we can actually plot it in a prettier way, so you can actually see what it really looks like. So some pretty cool stuff there, right? And then back here, recommended reading, the Practical Predictive Analytics, pretty good book. So basically around practical component analysis. Maybe my screw up on that one. So moving on to deliverable 4, basically Bayesian decision trees, and determining business rules. While we're doing that, I'm going to show one more thing. So I'm going to go ahead and start orange up. It takes quite a while, so I'll go ahead and kick it off. Back to the assignment. So deliverable 4, using Bayes decision trees to determine business rules. And this is where I get confused with this one, because they're different things. Apply Bayesian networks to solve a problem. There'd be some bonus points in that if I could give out bonus points to actually see if it could be done. Instead, what you're going to do is talk about Bayes networks and then talk about decision trees. So you're a data scientist working at Frostbite Falls Bank. Your bank has collected a large quantity of data regarding loans at the time of origination and whether or not the loan was repaid or defaulted. Your bank is interested in doing an SQL query from a database that will return a list of all the customers that are low risk. So they want to do some targeting marketing here. Pretty good idea. Your manager, Paul Freeze, has asked you to generate a decision tree model that will predict loan loss probability. From the decision tree output, you will determine Bayesian rules that predict low risk. The rules need to have at least 2 variables. So maybe I misspoke earlier. We'll see. Because it didn't seem like the 2 things made sense, because it's not exactly Bayesian. I guess you could say that the combination of those rules together in a chained fashion is Bayesian. But it's not a Bayesian network, right? Anyway, follow the steps below to model to predict the probability of default. Select one or more of the following programming languages, SAS, Python, or R, as we always do. Mastery is achieved by doing 2 or more. So 2 is good. For each chosen programming language, do the following. Create a decision tree model that predicts loan loss. Identify one or more nodes from the tree that has a low risk of default. Describe the node in a business rule. For example, a low-risk person will have less than 2 inquiries, debt-to-income ratio of under 20, and no more than 1 late payment. So you need to interpret that tree into a understandable sort of rule. Discuss whether the business rules make sense. Assess whether the chosen language or modeling approach had any effect on the variables selected. So just as I was kind of noticing some similarities and perhaps some differences between the things produced by Python and R, you might want to do something similar. So what do you turn in? A separate text file or source file for each of the programming languages, be it an IPython file or whatever, IPython notebook or whatever, a Word document with screenshot programming outputs of each and some things that add color commentary, an image of the decision tree generated for each language, then write a memo in a MS Word doc to your manager discussing low-risk segments found in the decision tree. Present nodes or nodes as business rules. Comment on whether the rules make sense. Comment on whether there is any difference in the rules generated by the decision trees or different analytics languages. So again, I'm back to where I was before. I don't think this has anything to do with Bayesian networks, right? And if I'm totally off here, let me know. Let me know what I'm misunderstanding, because I what I see here is created a decision tree and output the rules that are derived from that decision tree, not a Bayes network. So I must be missing something. The data exploration, we've talked about this data set before. Bad tells you if it's defaulted, it's 1 if it is. Then we have job other, so it has a job not listed, and so on. A job exec has an executive level job. Job manager has a manager level job. Job self is self-employed. Job sales is a salesperson. Office is an office person. Flag debt loan has a debt consolidation loan. So they've tried to reduce their debt by getting consolidation debt. A loan is the amount of the loan that you're going for. The credit line, age and months, the number of credit cards, the debt to income ratio, the number of delinquent payments in the last 3 years, the number of defaulted debts in the last 3 years, how much is still owed on their house mortgage, the value of the number of credit inquiries in the last 6 months, the value of their home, years working at their current job. And then the ones that start with the M underscore means that they were missing and had been fixed. Your rubric, quite a few criteria. So the first one is the source codes in multiple programming languages is well written. Screenshots are provided in the Word document and show a full understanding of accurate output. Decision tree for multiple programming languages is accurate and well written. Clear and thorough discussion of low-risk segments found in the decision tree. So you call out the ones that are the lowest risk. Clear and thorough presentation of the nodes or node as a business rule. So you are able to translate those nodes into rules that are understandable, and a clear and thorough commentary on whether the rules make sense, or is it just some statistical anomaly, or does it jive with your understanding of why someone might actually be in that situation. And a clear and thorough commentary on whether there was any difference in the rules generated by the decision trees in different analytics languages or programs, and if there are, why. So I made a point of trying to start orange earlier, and oh, there it is. Was not seeing it. So with that, just to finish out what I was doing earlier, we're to the end, right? So this would be where I say if you have any questions, but I want to show you something else first. So let's open up, and again, a decision tree. Again, I probably named that poorly. Where did it go? All right, yeah, let's, oh, no, I didn't. So this is Orange, if you're not familiar with it, Orange Data Science. Very kind of cool program. Probably you're familiar with it. Most of you probably have seen it at this point. So Orange, Orange Data Mining, sorry, not Data Science, comes out of, I forget what university, University of, I can't say that, Libidulania or something. Anyway, very cool product that came out of an educational environment. It's open source data visualization. Seems to be based upon some stuff I've seen. I think internally it's actually running R. Kind of interesting that it is. But why are we taking so long to come up? That's probably why. Okay, so data mining tool, you can download it from orangedatamining.com. Pretty cool sort of thing. It's drag and drop analytics. Not the most powerful thing you'll ever see, but pretty cool. So in this case, what I did was I dropped a file object on here, and I did nothing more than just drag over file. I double clicked on it, and for some reason it likes to pop windows. I navigated to the bizloan_ras file, CSV, that we use pretty much all the time. Once I did that, I went through here, and this is the part that's a little different if you're not familiar with R or with Orange. You basically decide, you tell it what the target is in the case of something that is essentially classification. The other things are features, so you can switch it whenever you click on it. Initially, it actually came in as a feature because it just thought it was a number. But you click on it, tell it, no, this is the thing you care about, and you do apply. And what that does is says, this is what I'm going to be trying to do. The rest of these, so that's your Y, right? The rest of these are X, and it's smart enough to do the right thing. I then used this test and score control to basically, what it does for you is you can link it to a file, and then you can connect multiple essentially learners or classifiers to it. So in this case, I connected a naive Bayes and a tree, a decision tree. And then I basically, it'll run it and it'll tell you essentially things like precision, recall, F1, and so on for each of the models that you've supplied it with on the data that you've given it. So these didn't do too bad, but it's not exactly something you'd write home about, right? And you can also, if you're so inclined, hook it up to a confusion matrix so you can actually see where it's getting it right and where it's getting it wrong per classification approach. And you can learn from that, and it's not doing too fantastic on the bad, right? Which is kind of what you really care about. Although you can see it as probabilities, right? So maybe that'll help. There we go. So I guess it's not fantastic, right? It did on the true the good goods, it did pretty good, but I wouldn't write home about the predictions on the actual bad and the real bad, and it's not fantastic. Anyway, so to show this a slightly different way, I'll go ahead and drop another file on. I'll go ahead and make sure that it is set. Oh, it originally came in a categorical, and it is target, so we will say it's categorical and target. And then do a, I'll do it this way, it's a little easier. Or split or sample. Data sampler. Data sampler is how you do your test train split. So I'm going to say I want 80%, if I can drag it, 80% will be my training, and the remaining will be the test. And then I go and drag from that to a, we'll say, decision tree. And we click on here to say that it is the data sample is to the data. So that is the 80% are going to go into the tree. And then we're going to want a score or a confusion. Wait, let me think. Predictions, that's what it is. And we drag here to the predictions as well. And then here we switch it from the remaining data is the data for the predictions. And we can also, up on the tree, do a tree viewer, so it'll show us the view of the rules that it comes up with. And looks like I need to work on getting it where you can see it. There we go. Zoom way out. Okay, and that tells me we need to get rid of those M values, right? So we can also drag this over a little bit, delete that line, drag a little bit, and select the columns that we want. And then take that over to the data sampler. We'll go in here and say, well, what columns do we want to get? So we don't care about all this stuff. It doesn't help. And probably don't care about this stuff. Probably doesn't really help. Although could, but we'll for now leave those out because that's what we typically do in the other. And then we can take a look at the tree now, and hopefully I need to close it and reopen it maybe. All right, controls and I are not getting along today. There we go. We'll go 5 levels. That's what's going on. So we come in, and the top one appears to be Um, trying to dig this out a little bit. There we go. So late payment appears to be kind of the most, especially when we're talking about good, right? So that seems to be pretty predictive of not forfeiting, so the lowest risk. And so you're looking 80, 85, 90. 94 is kind of where my mind would go, followed by 92. So CLNO and debt income ratio, I'm assuming that is. So kind of interesting. We can also then come out of here and do our confusion matrix and see how well this did in this scenario. And again, it should be the same rough as the actuals that we saw before, because we didn't really do anything different doing the same sort of classification. We're just doing it as you might actually do this in a real sort of situation. Also, you can modify the tree's settings. So you can say the number of instances of leaves. So is it a binary split, or do you want something more than binary? And do you want, how big does it need to be, and what's the maximum tree depth? 100 is like way too high for this problem, right? So let's take that down to 20. And you see that little blink it did, things went red and then it updated it. So now we should have a slightly different take on it. You can actually then take it down to maybe 5 or something, because you want to keep a tree pretty simple. And then at that point, we can actually, if we take that up, it shouldn't show us anything because 5 should be it, right? So if we go to 6, then down to 5, and then at the point you go to 4, you actually start seeing less things, right? So we've limited our tree depth, and we've still got a split that is either, it's binary in nature, it's either late payment is greater than or less than 80, 0.8, and then so on. So another way of looking at this problem in a very graphical sort of way, where it gets pretty interesting, is if you start throwing in some additional approaches to your testing, right? So you can grab here, drag out, and it presents with you things it thinks may make sense as other ways of doing it, and you typically want to stick to that same kind of color. And so maybe what does that do? I think that's the other approach. The CN2 rule induction is the way that generally whenever you're using the orange libraries in Python, which you sometimes do, how it actually produces the rules. And we'll see if that actually completes or not. While it's doing that, you can do other things as well. Go on down to something like I think ADA Boost is one of the ones that does really well. And so we can see here, doesn't like something, or it's still working on it. So at this point it's actually running, and this is where you can start poking around and learning something interesting, like I'm opening up Task Manager, so my screen kind of flickered, and I'm pretty sure, and it's definitely liking my CPU, it's not using the GPU at all. No, in this case it's actually showing that it's running Python. In the past I've seen an R logo, which made me think it might have been R, but no, it seems to be Python, which I would have thought, but sometimes things aren't always what you think they are. Yeah, there's no R running, so it's definitely that. But you can also tell here too, it's not taking advantage of the more powerful things in my computer, right? My GPU. This is not a wimpy GPU, and it's not using it. So either the algorithms they're using doesn't make sense to use a GPU, or else it's not that smart. So anyway, so with that, I've pretty well talked for a while. It sounds like somebody joined or left. Either way. So anyway, I guess we're at time. Uh, I'll let this keep running for a while, and if you're interested, ping me, and I'll let you know what the end result was. Otherwise, stay safe. If you have any questions, let me know. Shoot me an email, text message, whatever. I'll be glad to respond. If you have any questions about the assignment, let me know. And don't get too confused by the Bayes network stuff, because the deliverables do not seem to support that name. Rather, it's about a decision tree, and then being able to interpret those the outcome of those rules in a way that is something a business analyst could apply. So with that, I'll wrap this up. If you have any questions, let me know. That's what I'm here for. Stay safe, and we'll talk again next week. And have a good weekend if I don't hear from you before then.